Okay, good morning, everybody. So I'm Alice Sitch. I lead the laboratory studies section of the NIHR statistics group. And we also have Dawn here who is the co-lead for the entire NIHR statistics group, and it's the two of us that will be talking to you today. So just a very brief introduction to what we're going to do in the session today and to the NIHR statistics group as a whole. So one of our main aims is to really bring people together. So not just statisticians, but actually bringing together people from laboratory sciences and trying to do some more educational pieces and just understanding the problems so we can come up with some good solutions to those together. So it's really good to see a nice turnout for this session. We were told that there would be a gap in the market for this, especially at the moment for some of you that might be coming up to some exams. So hopefully you'll find this useful, and we'd really appreciate any feedback about this and on any topics that you think might be helpful in the future. So if there's anything that we can develop for you that would help you, and if we can sort of establish going forward. Okay, so you'll see there are lots of working groups for the NIHR statistics group. So it is a bit broader than just the laboratory studies work that we are kind of trying to bridge the gap with in our particular section. There are lots of other elements to it as well. So please do visit the website and have a look at some of the information available on the different groups. If you are interested in those, so all of the groups tend to hold events throughout the year, so just have a look and keep an eye on those if there's anything you would like to attend. So today's session, we've just got the two different presentations today, and hopefully there'll be lots of time for any questions you might have as well. So I'm going to start off. We're going to be talking about how you choose the statistical test that you would use and understanding p-values. Now, confidence intervals have to creep in a little bit there. So we're going to have a bit of a focus on p-values and also their link to confidence intervals and what confidence intervals are. And then Dawn's going to show you some really nice novel ways of displaying data. So actually using forest plots. So that's really nice and interesting way of visualizing the results that you've got. So it links very nicely from the end of my session, where you'll be looking at p-values, confidence intervals, and displaying your results. So just a little bit of housekeeping for the session. If you want to ask any questions, we will probably have some time today where we can ask questions. So if you have anything, you might be able to unmute yourself and we can take questions in that particular part of the session. But if there's anything you want to ask via the chat, please do use that function and we'll pick that back up when it comes to an appropriate time to work through those questions. And as some of you have asked, and you may have seen the box pop up, we are recording this session and we will try to make it available via the NIHR Statistics Group webpage as soon as possible. So there is a little bit of processing that needs to be done, but we'll try and make that available to you when we can. Okay, if you would like to know more about future events that we are going to do, then there is a mailing list that you can join. So I've already put this in the chat once, so some of you may have seen it, but just to make sure everyone that's here now has got it, I'll repost that. So if you click on that link, it will allow you to actually sign up to be on the mailing list, and you can leave that whenever you want. So if you sign up and you realize it's not your cup of tea, then you can leave whenever you wish to. But if you do want to know about future events, then that's what we've got there. That's just for the laboratory studies section. It's not for the entire NIHR stats group. Okay, so that's the introduction. I'll just grab my slides for my part of the session and then we'll get going with that. Okay. Can everybody see my slides again now?
Yes, that's great.
Thank you, Dawn. Okay, so how do we choose the right test? And we're going to think about some p-values. So this session very nicely sort of separates into two parts. So we're going to think about how we choose the right test, and then we're going to think about interpreting the results from whatever that test is that you've chosen. So often you end up with a p-value. That's kind of common across tests. So we've got these two different sections. So we're going to start off by thinking about which is the right test that we can choose. So what are the questions that we ask ourselves to get to that right selection of a test? And then we're going to think about the interpretation separately. So the things that we consider when we are choosing the right test, and I'm going to start off with the simplest situation you might be carrying out a test in. So this is when you're trying to compare two groups. So this is the sort of very classic way that you will have probably been introduced to testing. So when we have two groups that we want to compare, the kind of things that we'll be thinking of are, what is the variable type of my outcome? Okay, so do I have a continuous outcome that I'm comparing between my two groups? So am I calculating a mean for the one group and a mean for the other group and trying to compare those? Or is it that I have a binary outcome? So I know the percentage of people in one group that have got an event and the percentage of people in the other group that have got an event. So I'm comparing the percentages or the proportions across those groups. So that's really key to understand the outcome. And even though I'm going to introduce this to you as a comparison of two groups, because that's the sort of the way that we would often use some of these tests, actually understanding the variable type of your outcome is the first thing I always think of when I'm selecting any kind of analysis. So even when you go into modeling, when you go into perhaps a more sophisticated analysis than a basic test, you would still want to think about what is that outcome that you're comparing and what is the variable type of that outcome. That's very much the key question to lead you into the right kind of analysis. So after I've established that, I'm often then thinking about the structure of my data. So is there any structure to my data? The two groups that I'm comparing, are they, is it a before and an after measurement for the same individuals? Or is it that we have two completely independent groups that we're comparing? So that's really key to try and understand, do you have that independence of the two groups that we're looking across? Or is it that there is a connection between the two and there's some structure to the data that you need to take account of? So is it that it's paired? Is it that you've got observations at two different time points or very similar observations? Perhaps you've got whether somebody is positive or negative on a PCR test and positive or negative on a lateral flow test for COVID or something like that. So you would expect there to be some correlation between those results if that was the case. So it's really trying to understand if the groups that you have that structure in there or if you have got complete independence, and that will lead you to the correct kind of test that you will use as well. When we have continuous data, we're often quite concerned with the distribution of our outcome. So when we've got a numeric outcome for whatever it is that we're looking to compare across our groups, then we will be trying to make sure that we fulfill the assumptions of certain tests. So we're often looking to see, is that continuous outcome approximately normally distributed? And if we don't have that, if we don't have data that's approximately normally distributed, then we have got a couple of options. So we can try to put in a transformation to see if we can get that data to be approximately normally distributed, and then we can carry on using our standard tests that rely on the assumption of normality. If we don't have that and we can't do a transformation, perhaps none of the transformations seem to make the distribution any more normal, or perhaps there's another reason why you really want to keep it in the original format, then we do have some non-parametric alternatives. So they don't rely on that assumption of normality. So we'll go through what they would be if you do find yourself in that situation. And then there's a sort of another consideration that we sometimes have to think about, which is sample size, and we'll go through exactly what that means for the different kinds of tests that we'll investigate. So trying to map this out, and again, this is for a comparison between two groups here, and I will elaborate a little bit more on what happens if you haven't got a comparison between two groups in the next slide, but just taking you through the decisions that I would make if I was selecting the right test. So first of all, what is the outcome type? So this really is the most important question, and this isn't just for a two group comparison, this is across all of the sort of analyses that you might do. I'm always thinking about what is the outcome and what is the outcome type, and that sets me up then to really think about the type of analysis that I am going to do. So let's start off by saying that we've identified that we have a continuous outcome. So it's a numeric value that we are getting, and that's what we want to compare between the two groups. So we might be hoping we can calculate a mean and compare those between the two groups, and that's where the situation we're in. So we have a continuous outcome here. So the next thing we need to ask ourselves is that approximately normally distributed? Now, as I said before, if the answer is no, then we can look at a transformation, and then we can go down the sort of saying that it's yes. So you can say no, but then after transformation, we loop back around and we say that we do now have data that we can treat as approximately normally distributed because it's gone through that transformation. So if we say that, yes, we do have approximately normally distributed data, then you might want to be asking yourself, is that data paired? So is it that you've got two observations for each individual, one's at a baseline, one's at a follow-up? So that would definitely be our paired data there. So you can just look across the values for an individual. Or is it that they're completely different groups? Are we looking at values in a group of smokers and a group of non-smokers? So they are completely independent, they are different people, and we can look at those as totally separate, independent groups. So that's the next question we have to ask ourselves. So is the data paired? Okay, and then to some degree, this question, when we're thinking about our continuous outcomes and the tests to look at differences between two groups for a continuous outcome, the sample size question isn't actually too important. So I'll explain why I'm saying that. So if you say that you have got paired data and it's approximately normally distributed with your continuous outcome, then you're looking at a paired test. And this could be a paired t-test or a paired z-test. Now, the difference between these two becomes very, very small when you have a large enough sample. So when you have over sort of 20 participants, then you would have a large enough sample that your paired t-test is actually almost the same as your z-test. And this is because the t distribution, so the t-test is based on the t distribution, it has an allowance for when you've got a very small sample, it gives a bit more weighting to the tail. So it allows you to have these more extreme results that you might well see when you have a very small sample. So it's a case that the t-test actually is appropriate for all sample sizes, and that's what usually you see people do. They use the t-test. They don't say, oh, I'm doing a z-test instead because I've got 25 participants. They would just use the z-test for, sorry, the t-test for all. It's just that after you've got a reasonable number of participants, it converges to the z-test. It will give you the same result, and that's because the t distribution converges to the normal distribution after you've got a reasonable number of participants. So some people will say anything over sort of 20, you're getting a very similar result there. So you could just say that the sample size bit doesn't really matter here. You could just use the t-test for all of these, and that will make sure that you allow for having a small sample if you do have a small sample, and it will just be giving you a similar result or the same results depending on how big your sample is, as the Z test would. So it's very much a technical point that you've got the t-test and the Z test there, depending on the sample size, but most people in practice would just use the t-test for all. So it's just so you know that it approximates the test using the normal distribution instead after you get a large enough sample. If you haven't got paired data, then we're still thinking about our t-tests, and it's just that it's a 2-sample t-test instead. So another name for the paired t-test is actually a 1-sample t-test. So this is because you can actually, instead of having those 2 groups, you can work out the difference. So what's the difference between the follow-up and the baseline measurement for each individual? And you can compare that to 0. So you can reduce it down to 1 sample and compare that to 0. Whereas when you have the 2-sample t-test, you're calculating the mean for each group and you're looking at what is the difference between those. So it's the structure of the data that's really driving the difference between those two. And then the you'll probably see in practice that most people would refer to these as t-tests rather than z-tests, but just so you know, if you do see a z-test, it's the same thing as long as you've got a large enough sample that you didn't need that t-distribution to account for the variability in the tails you might see with a small sample. Okay, so that's going down the yes for our approximately normally distributed branch there. If we don't have that, and perhaps there is no transformation that will help us here, then we are starting to look at our non-parametric alternatives. So again, we do need to ask ourselves about whether we have the structure in our data. So is it paired? If we do have pairing in our data, then we can use what's called the Wilcoxon-signed rank test. So you can think of the Wilcoxon-signed rank test as the non-parametric alternative to the paired t-test. So this is how I sort of remember them, is I pair them off. So you've got the paired t-test. The non-parametric alternative that does the same thing in the same situation is the Wilcoxon-signed rank test. If you haven't got that structure in your data, so you've got the independence again, then it's the Mann-Whitney U-test is the non-parametric alternative. So again, thinking about pairing this up with the parametric test, it would be paired with the 2-sample t-test. So that's the 2 that you can do when you have no pairing of your data. So you've got your independent groups, but the 2-sample t-test is for when you have that assumption that's met, that normality assumption, and when you don't have it met, so you have to have the non-parametric alternative, it's the Mann-Whitney U-test instead. Okay. So thinking about the other kind of outcome that we might come across when we're comparing 2 groups, so we have a binary or categorical outcome. So we have to ask ourselves about whether the data is paired here. And so this is around the independence, or whether we can assume that there might be independence around those measurements that we're looking at. So the example I used before was when you've got 2 different types of tests that are trying to pick up the same disease. So you would expect that there's some correlation with being positive on one of those tests and being positive on the other. So if that's the case you're in, we would say that that's pairing of that data again. So that's when we would use McNemar's test. So that is when you've got that structure of the data, when you haven't got, when you've definitely got that correlation between them. And so you need to allow for that, and you would use McNemar's test. If you don't feel that that's something you have in your data, so you're actually not looking at that, then you can think about your chi-squared tests, your straightforward chi-squared tests. So there is a further consideration about sample size, and this is around whether you've got a reasonable number of people in each of the combinations that you've got. So when you would draw up a contingency table to actually look across these, you can think about how many observations do you have in some of those cells. And if that's very small, then we do have ways of allowing for this. So you could do Fisher's exact test, which will allow for the fact that you've got a small number of observations in some of those. If you don't have an issue with that, so if you have a reasonable number of observations for each of the cells, then you can be thinking about your chi-squared test. And if it's that you're looking at an outcome that has a trend, so it has certain levels, and you're happy with that assumption, then you can actually expand that to the chi-squared test for trend, which will allow you to use that assumption of going through the categories there. Okay, so that's the process that I go through when I'm trying to select the appropriate test for those kind of situations. Obviously, it can be a bit more complex than that. So we've been looking at 2 groups there. If you've got more than 2 groups, so you can expand looking at your continuous outcomes to having ANOVA. So you can do ANOVA when you've got more than 2 groups. So that's the comparison of means. If you don't fulfill the assumption of normality, the non-parametric alternative to ANOVA is the Kruskal-Wallis test. And just to say that you can actually use modeling for all of these instead. So when you start to think about adjusting for other variables, or if you have clustering, so you have some sort of structure in your data that you want to allow for, then you will often see people use modeling instead. And if you are trying to compare your continuous outcome across a continuous variable, or your binary or categorical outcome across a continuous variable, then that's when you will most likely go to modeling as well. So just to note that the type of model that you choose is again predominantly driven from the kind of outcome that you have. So the intricacies of what you do in that model might be from exactly the research question that you're asking and what you're trying to understand from the data that you have. But the choice of outcome is really driving that selection firstly. So if you have a continuous outcome and we want to use a modeling approach, it will be a linear regression model. Obviously, there are certain assumptions you need to fill around that, but that's where we would start looking with our analysis. If you have a binary outcome, then you're looking towards a logistic regression model. And there are some other options for you if you have categorical data. So you can use a multinomial model or an ordinal logistic regression model, but that requires you to have an outcome where you're happy to have those jumps between the categories. So that's pushing us a little bit further into more sophisticated analyses. So, okay, but the main point really is that it's that data type of the outcome is really key for deciding the kind of analysis that you're going to do, and that's with the simple tests and with the more sophisticated analyses. And when you start thinking about modeling as well, that's really important to make sure you're happy with that. So that takes us to the end of the choosing the correct tests section. So I'm going to move on now to thinking about our hypothesis tests. So I'm going to go through an example, and we're going to pick it apart and really set up the hypothesis test that we're doing. Think about the concept of p-values and how we would actually interpret those, and what else we need to think about when we fully interpret the results of a test. So we need to start off with a research question. It's always very important that when you're doing any kind of hypothesis testing, you clearly understand the research question that you're trying to answer. So in this particular case, we have a study where we are randomizing children to receive an education program or they don't receive an education program. The aim of that education program is to get them to reduce their salt intake. So we have some analysis of their urine at the end of the trial, and we see, is it that so that what we want to happen is those that have gone through the education program actually have a reduced intake of salt compared to those that haven't. So we're going to look at the results of their salt intake and see if there is any difference between the two. And that's the reference there. So if you'd like to look at this paper, that's where it is. It was published in the BMJ in 2015. So the research question is there a difference in the salt intake of those receiving the programme and those not receiving the programme? Okay, and this is the main result from the abstract. So I'm just going to pick up on the important things that we really need to be able to understand from that. So this 1.9 grams per day, and it's negative 1.9 grams per day. So that is telling us that there's a reduction of 1.9 grams per day on average, and this is comparing the intervention group to the control group. We then have a 95% confidence interval, so it's telling us the range of values that we may well see if we were to repeat this study again. So we're saying, well, it could be a reduction of 2.6, it could be a reduction of 1.3 grams per day. And then we have this p-value, which is reported as less than 0.001. So we're really going to get to grips and make sure that we understand all the different components of this result that we've been given here. So when we're setting up a hypothesis test, there's quite a few steps that we need to go through. And some of these are just sort of, we need to be aware of them in order to make sure that we can assess the evidence in the appropriate way. So we're going to go through each of those step by step. So we'll start off specifying the null and the alternative hypothesis. So in most cases, our null hypothesis and our alternative hypothesis the alternative hypothesis doesn't specify any direction. So when we have our standard hypothesis testing, we aren't specifying the direction of the effect. So the null hypothesis here would be that there is no difference, and the alternative hypothesis would be that there is a difference. There are some very special kind of studies where you might specify the direction of the effect, but most studies that isn't the case. And in most studies that are set up, our null hypothesis is that there's no difference, and the alternative hypothesis is simply that there is a difference, and we don't specify the direction of that effect. Even if you've actually, you're doing this education program with the view that it will help reduce the salt intake, we start off in equipoise, so we don't know what's going to happen, and this is how we would set up our null and our alternative hypothesis. So bringing that back to our example that we have, the null hypothesis would be that there's no difference in the salt intake of children in the intervention group and the control group, so those receiving the program and those not receiving it. And the alternative hypothesis would be that there is a difference between those receiving the program and those not receiving the program. So it's important to really know what our null hypothesis is, because we have to assume that it's true. That's the next step in actually carrying out our hypothesis test. So we assume the null hypothesis is true. We assume that there is no difference between our two groups. We have to use that assumption because we are comparing our data. So the data that we've observed, we compare back to what we would see under the null hypothesis. So how different is our observed data to what we would expect to see if the null hypothesis were true? So how different is the observed data to what we would see if there was no difference? Now, exactly how we measure how far away our data is from what we would have expected to see under the null, that depends on the kind of test being performed. So this is how you generate the test statistic. So it's different for if you're doing a chi-squared test, if you're doing a t-test, and it's a slightly different way of doing it, but you can think of it for all of these tests as being a measure of how different is the data that we've observed to what we would have expected to see under the null hypothesis. Now, because the test statistic is different across all of the different tests that we can do and the way that we calculate it, what we will do for these tests is actually convert it to a p-value. And the p-value is something that we get across all the different tests that we will do. And so that's converting that difference between the observed data and what we would have expected to see under the null hypothesis to a probability. So it's probability. It can theoretically take a value from 0 to 1. And it's the probability that you've seen the data you've seen, or the difference that you've seen, or a more extreme difference if the null hypothesis is true. So what is the chance that we could have seen the difference we've seen, or even a bigger difference, if in fact there really is no difference, the null hypothesis is true? So how likely is it that the difference we've got could be observed if the null hypothesis is true? Now, it's a tricky concept to get hold of, and I know that people often try and remember, well, which one's significant? Is it above or below this certain cut point that you might be applying? But if you truly understand what that p-value means, then it becomes nice and obvious and quite intuitive what actually would be significant.
You know, like GMSs and things like that. Yeah, so
if you really think about it, you're saying, what is the probability I've seen of me seeing a result as extreme or more extreme than what I've actually detected from my observed data if the null hypothesis were true? Now, if that is like 90%, then you're saying, well, it's very likely you could have seen that difference if the null hypothesis were true. So you may well then think, well, the null hypothesis could still be true. 90% chance I'd have seen this if the null hypothesis were true. If that probability gets really, really small, so if that starts being 1% or 0.1% or 0.001%, then you're saying the chances of me seeing the result I've got or more extreme if the null hypothesis is true are absolutely tiny. Really, really small chance I'd have seen this if the null hypothesis were true. So when you get to that sort of situation, you're thinking, well, maybe the null hypothesis isn't true then. And that's the evidence you've got to think about whether you've got sufficient evidence to say that you don't believe the null hypothesis is true. You don't think the null hypothesis could be true given the result that you've seen. Okay, so this is where it really comes into assessing the evidence. So we've got our p-value, and now we need to think about what that means. So people use statistical significance. You see it all the time in papers. There is a slight shift away from using the cut points for statistical significance. And I would encourage you all to think about p-values across their entire scale. So they are probabilities, they range from 0 to 1. But think about, it's not all about that dichotomy. So the smaller that p-value, you're saying the chances of you seeing that result are more extreme if the null hypothesis is true, is getting smaller and smaller and smaller and smaller and smaller. So when you're in this kind of region, when p is less than 0.001, that's very strong evidence against that null hypothesis. Okay, as that p-value gets larger, then you're less convinced. Okay, so at the point where it's a 10% chance or more that you'd see that result or more extreme under the null hypothesis, then we're not as convinced that that null hypothesis couldn't be correct. Okay, so please do think about your p-values on the whole scale. It's not all about this magic cut point, and that the smaller that p-value goes, the stronger the evidence is that the null hypothesis shouldn't hold, that the null hypothesis isn't true. Okay. So statistical significance, this is when we use a cut point for the p-value. So we set a level of statistical significance. Often this is 5%. So we set ourselves a level that we're willing to be wrong. Okay. So at 5%, we are saying, well, we're going to say something is statistically significant if there's less than a 5% chance of seeing that result, or more extreme, if the null hypothesis is actually true. So we're allowing ourselves to be to that level of being incorrect. Okay, and then we can interpret it as such, and you will see these in some studies. So my plea to you, and I think the statistical community as a whole, is to not be quite so not use them in quite the way that they have been used. It isn't that there's something magic about that point. It's just that often we want to use something, but please do think that a p-value of 5.1% isn't that different to a p-value of 4.9%. So think about it. Even if you are using a statistical significance cut point, just think about if you have got a borderline result and interpret it as such. So it's very different compared to a p-value of less than 0.001. Okay. Now, there's some caution about if you get a result that you would consider to not be statistically significant. So this is absence of evidence is not evidence of absence. So your p-value is always telling you how much evidence you have against the null hypothesis. So always think of it in that way. If you end up with a p-value of 0.7, say you're saying, well, there's a 70% chance that I'd see this result or more extreme under the null hypothesis, so there's not sufficient evidence for me to reject the null hypothesis, that does not mean that your two groups are the same. Okay, so we haven't set our hypothesis up to look for equivalence in that way. In this example, and across most examples, you very rarely see tests of equivalence. So please don't overinterpret a non-significant result as meaning that your two groups are the same. So just to issue a word of caution around that. Okay, so back to our example and thinking about how we would assess the result here. So we've got our p-value of less than 0.001. So the probability that we get the result we've seen, so the difference between the groups that we've seen, or a more extreme difference by chance, is less than 0.001. Okay, so that's very small. And if we were using the 5% level, it's below 0.05. So we would say it's a statistically significant result at that level. It's very strong evidence against the null hypothesis that we've got there, because it's this less than 0.001 value. Okay, so I would argue that we haven't fully interpreted our result there. We've looked at the p-value, but we haven't said anything about how different those two groups are. We haven't used that estimate of the difference between the two groups, and we haven't thought about what might happen if we rolled this out in practice. So statistical significance, that's the p-value, and we're really thinking about whether there's an effect. There is no comment on the size of the effect. It's a purely statistically driven outcome for your study. Now, clinical importance, how do we assess that? Well, this is from your estimates. So what is the estimate of the difference between the groups, and what's the confidence interval? So that's telling us about the uncertainty of our estimate of that difference. So from that, we can think about whether the effects are they important? Are they large enough to actually demonstrate importance? Is it that we're picking up a statistical difference that's meaningless? So we could find a very, very small difference that's statistically significant and wouldn't actually make any difference if we managed to deliver that in our population. So while statistical significance is important and we should consider it, there's clinical importance as well that is more important in many ways. Okay. So an extra note on confidence intervals. So they rely on the normal distribution. They help us to describe uncertainty. You may have seen them used with reference ranges, but they're also used with confidence intervals, which is what we're going to focus on for today. So when we take a sample for a study, we want to obtain an estimate on that sample. If we were to take another sample, so say it was a sample of 100 participants, if we were to take another sample of 100 participants, then we would expect to see a different answer. So if we calculate the mean from the second 100 participants, we'll get a slightly different answer, but we can work out how different we expect it to be for each one of those samples that we might take. Okay. So the way that we do this is by thinking about the standard error. So the standard error is telling us about the variability, not in the samples themselves, but in the population that we've measured. So in that sample of 100. So let me say that again, because I'm not sure that was too clear. When we have our first sample of 100, the standard deviation will tell us about the variability of the measurement in that sample of 100. The standard error will tell us about how different we expect the mean value to be across lots and lots of repetitions of that sample of 100. Okay, so confidence intervals use the standard error and tell us the likely range of values that we might see if we were to repeat our study again. So if we were to go and get that next sample of 100 and a next sample of 100, how much variability do we expect to see? Not in the whatever it is you're measuring itself, that would be the standard deviation that would tell you about the variability of that, but in the mean value of it, if that was what you were trying to calculate. So in the estimate of the outcome that you're trying to derive from each of the samples. Okay, so this is our standard normal distribution that you may have come across before. So when we are working with the standard normal distribution, we actually reduce it down. So we're thinking about 0 being in the middle, and we're thinking about z-scores. So this is how far away are we in terms of, so how far away from the mean are we in terms of standard deviations. So a standard normal distribution has a mean of 0 and a standard deviation of 1. So you may well have used these to come up with reference ranges. So you're thinking about being 1.96 standard deviations away from the mean value, and that will give you 2.5% in each tail. And you may well have thought about these to give you a reference range. So you've got 95% of your measurements in the middle and 2.5% in each of those tails. Now, when we are thinking about a confidence interval, it's not the original values that we're putting on that normal distribution curve. We are thinking about the estimates from repeated samples that form their own normal distribution. So this is the sampling distribution. So we're not actually going to do this, but if you imagine that you got your sample of 100, calculated a mean, plotted it on this graph, and then you did that over and over again. So another sample of 100, calculate a mean, plot it. Sample of 100, calculate mean, plot it. So we keep doing that. Those mean values form this distribution, which will be normal distribution, and that's called the sampling distribution. This is how we calculate the standard error for a mean. It does vary when you're calculating different estimates from a sample. So we use that theory, that same theory you've seen with reference ranges, to actually say that this is what will happen to your sampling distribution, and instead of the standard deviation, it's the standard error. So it's telling you about how your estimates will be distributed rather than the individual data points. Okay, And as we've said, you will do this for your one sample. So you will calculate your one sample of 100 participants, you'll calculate the mean, you'll put a confidence interval around that, or you'll calculate relative risk, put a confidence interval around that, an odds ratio, you could calculate a mean difference, whatever it is, whatever the estimate is, you'll calculate it and put a confidence interval around that. Now, depending on if you went out and got another sample, you'd see that you would get a slightly different result. So what we actually would say when we interpret our confidence interval is that if you were to go and repeat your study over and over and over and over again, that 95% of the confidence intervals that you would calculate would contain the true estimate of the mean at some point in the width of that confidence interval. Okay, people generally tend to go with a slightly less rigorous interpretation of confidence intervals. So they will talk about it providing you with a range of uncertainty, so likely values and that kind of thing. They'll talk about being 95% confident that the result would be from the bottom to the top of that confidence interval. But we're really, the theory is thinking about if you were to repeat it with the same size sample again and again and again, what would happen with those. Okay, so bringing us back to our SALT example and making sure we interpret that fully. So the estimate was a reduction of 1.9 grams per day. So we would need to consult with clinical colleagues to know if that was an important difference. And we could then think about whether even though we've got a statistically significant result, is that meaningful? Would a reduction of 1.9 grams a day have a meaningful effect on these children? And that 95% confidence interval, so it ranges from a reduction of 1.3 grams a day to a reduction of 2.6 grams per day. So again, we can really think about if we were to get those results, so that's if we were to repeat that study, we're thinking that we could perhaps see a reduction of 1.3 grams a day, we could see a reduction of 2.6 grams per day. Would they be meaningful? And we can really think about that fully when we've thought about the confidence interval, and if we do know a minimal clinically important difference that we're looking to detect here. Okay, how do our p-values relate to our confidence intervals? So when you calculate a confidence interval, that's a 95% confidence interval, these relate back to p-values at the 5% level. Okay, if you were to calculate 99% confidence intervals, these would relate to p-values at the 1% level. But most often you see 95% confidence intervals and we are considering p-values at the 5% level. When I refer to the null value, this is the value that would indicate there's no difference. So if you were looking at a mean difference, this would be 0. If you were looking at a relative risk, this would be 1. If you're looking at an odds ratio, it would be 1. So for any relative measure, it would be 1. For any absolute difference, it would be 0. Okay, so if your 95% confidence interval contains the null value, then your p-value is actually greater than 5%. If your 95% confidence interval does not contain the null value, so the null value is outside of this, you see that the entire bound is one side or the other. So it's over this way here, but it could be that the lower bound was here and then it went up to here. That would be the same thing. So if it's outside, that null value is outside of the 95% confidence interval, then you do have a statistically significant result at the 5% level. So P is less than 0.05. And when that null value is right on the edge, and so again, it could be either bound that it's right on the edge of, then your p-value is exactly 0.05. Okay, so that brings me to the end of my presentation. I think there might be a couple of comments in the chat, so I'll have a look at those now. And then if anyone has any questions, please do let me know. So slides, we should be able to make the slides available via the same process. So we are recording this session, and we can try and make that available to you as soon as possible via the NIHR group website. So when is it appropriate for mean and median to be compared between groups? So if you're comparing means between two groups and you think it's appropriate to do so, so you've got that normality assumption, the mean is a meaningful measure to be able to look at, then you can do this with a t-test, and you can actually test for those differences between the means across the groups. If you're looking at a median for those two groups, then I'm assuming you're probably doing that because you've got outliers, or you've got skew, or you don't have that normality assumption being met. Then you're looking at either doing a transformation and going down the route of t-test if it's appropriate after transformation, or you might be looking to do one of your non-parametric tests instead. If you want to compare two groups, you do need the same measurement. So you wouldn't compare a mean in one group compared to a median in another. You would choose an appropriate measure for both. So if you find that you meet the assumptions for one and not the other, then you'd probably you'd go with the median for both, because you know you can calculate that across both of them. Okay. The considerations and how to assess normality in your data. Okay, so there are some tests for normality. So there's the Kolmogorov-Smirnov test that people sometimes use, and there are other tests as well. I wouldn't normally use them. So they are generally low powered. So I wouldn't automatically go to doing those tests to look for normality. What I would do instead is actually plot my data. So I would draw a histogram and I would visually inspect that data and see if it approximately followed a normal distribution. You can sometimes pick up noise with these tests, and so it's important to have a look at the data and really decide for yourself if you think it's reasonable to treat it as normally distributed. I know it's slightly easier when you get a number and you can apply a cut point, but a visual inspection is what most statisticians I know would do for assessing normality. How would we express 95% confidence interval equivalent for non-normal data? Okay, yes, it's a good question. You will see that when you do these non-parametric tests, you basically end up with a p-value, and you don't have the confidence interval to look at, so you can't really assess clinical meaning. So clinical, how is it in terms of being a reasonable difference that you get? So sometimes people will look at the difference in the medians, but you'd have to do that yourself. You'd have to calculate those difference in the medians yourself. For getting a 95% confidence interval equivalent, so my immediate thought goes to, you could probably express part of the range. So you could use some percentiles or something like that. You could go into a bootstrapping method, so a resampling method, to try and work out what the range might be, just cutting off those extremes, those 2.5%. But that's probably the best thing to approximate a 95% confidence interval, although we wouldn't call it that. We'd call it bootstrapped interval. I would say people don't often do that, so they'd probably more likely to give an interquartile range with a median, which would be reasonable. That's what you would usually see in a table 1 when you're explaining your baseline characteristics, the median and the interquartile range. That's the 25th percentile and the 75th percentile. Yeah, it's only if you were interested in the difference for something that you got a median for would I go towards the looking at the percentiles in any more in any more depth. Okay. Got a comment about looking at some different plots. Types of transformations for non-parametric data. So the log transformation is one that I would probably go to first of all, but there are others. So you can do square root transformations. You can look at different powers as well. There is a command in Stata, which is called the gladder command, which will just automatically look at all of the common transformations for you. And you can look at the plots of them. So you can just visually inspect which of the transformations looks to give you something that's the most sort of approximately normal. So that's often what I go to. And yes, there are some more complex ones as well that you can use. So it really just depends on the type, on the data that you've got and what suits it best. Sometimes the log transformation doesn't help, unfortunately, but there are a few others out there that are commonly used. Could I explain about the odds ratio? So the odds ratio isn't as nice as a relative risk, I suppose, is where I would start from with that. So relative risk is when you've got the probability of an event happening in one group and you divide that by the probability of an event happening in the other group. So probability of an event happening in the intervention compared back to the control, which would be the bit you divide by. So that would be the denominator. When you've got an odds ratio, you're taking the ratio of the odds instead, but the odds itself is already a ratio. So the odds of an event is the probability that an event occurs compared to the probability an event doesn't occur. So you would do that for the intervention group, that would be on the top, and you would do that for the comparator group, which would be on the bottom. That would be your denominator. So it's a ratio of ratios, and it becomes a little bit confusing. So I'd go back and have a look at some of the literature around that if you're interested in odds ratios. They're not as intuitive as risks. But yeah, it's the odds itself is probability of an event divided by the probability there isn't an event, and then you look at the ratio of those between your two groups, so intervention and control, if that's what you're looking at. Difference between paired and non-paired. So paired is when you have that structure in your data, so a before and after measurement on the same individuals, let's say, as an example. When it's not paired, we can think of those as being completely independent. So smokers versus non-smokers would be completely independent. Whereas if you had people that smoked at the beginning and they stopped smoking, so you looked at them 3 months after, they're not independent because it's the same people and it's just that they're smoking and they're non-smoking phase. So that's what you need to think about. Are these groups completely independent, or is that link there? Is it the same individuals that I'm measuring twice, say? How could we assess that test results on two different samples were the same? Okay, so I think you're asking about an equivalence test there. So you very rarely see those, but you can set up your null and alternative hypotheses in a different way, so that you are actually setting a bound around. So you're obviously your difference. So you can say, well, this is the value you get if the two groups were the same, but you're happy to say that they are still very, very similar if you set this bound around them that's really close. And you'll say, well, there's no actually meaningful effect if they're that close together. So you set what we call an equivalence bound around that, and then you can set your hypothesis up to ensure that the result is within that. So you would declare it as being equivalent if you were within that range. So you have to set up your test in a completely different way if you want to actually be able to make that conclusion that your two groups are the same. That's not what you see in most of the literature. So most of the tests that you see are set up the way we've looked at today, which is the two-sided tests. that you will get hold of. Did I mention that a paired t-test could also be called a one sample test? Yes. So this is because you can actually calculate the differences. So you'll have measurement 1 and measurement 2, say, and then you can calculate the difference for each individual, which brings it down to just being one sample of the differences, and you compare that to 0. So that's why it's also called a one sample t-test. But you might see that in textbooks and statistical packages where it's called one sample. So yes, that is a paired t-test. Why might we use a model over a test? So often they're actually that they can be the same thing. So a t-test and a basic linear regression model are actually equivalent. The benefit of modeling is you can make it broader. So you can actually start introducing confounding. If you've got any clustering in your data, you can allow for that. If you've got multiple things you want to allow for, it's just a bit more flexible, and it can really allow you to develop your analyses. So depending on the research question, depends on what you would end up doing. So we often end up with models because it's not that straightforward question that those simple tests are doing. So your t-test, your 2-sample t-test is just comparing the mean between 2 groups. That's all we can do with it. Whereas a model, a linear regression model, we can really develop it and say, well, what if we allow for all sorts of other characteristics of the individuals and the design of the study. So it just allows us to do a bit more with our data. Can I describe the difference between absolute risk and relative risk? So yes, when you're talking about an absolute difference in risk, so if you had the risk in one group was 10% and the risk in another group was 5%, the absolute difference between the two is 5%. So one of them is 5% greater than the other. It's 10% versus 5%. Whereas if we're looking at them in a relative way, we're not doing 1 minus the other, we're doing 1 divided by the other. So that 10% will be twice the 5%, or the 5% will be half of the 10%. So it's just the way you choose to compare those risks. Are you doing it as 1 minus the other, which would be your absolute risk difference? Or is it one relative to the other, which is when you'd start dividing them? A question about sample size for studies. So that depends on what the primary analysis would be and what you're looking to detect. So you set a level of power and you'd set a level of significance, and you would have to know what that primary comparison would be. And there's lots of statistical packages that would then allow you to say, well, if you do expect to see a difference of a certain magnitude, the number of people you would have to get to obtain that level of significance and power that you wish for. So tables for the normal and the t distribution, that they aren't different across the different tests. You go to the same table. It's the way that you apply it that changes. So for your 2-tailed and your 1-tailed tests, basically for your 2-tailed tests, because you're allowing for things in either direction, if you're using the 5% significance level, you're allowing your 2.5% in each of the tails. If you're doing a 1-tailed test and you're using a 5% significance level, you're allowing that 5% all in the 1 tail. So the value you would use is different, because you're not looking up the one that gives you 2.5% in the tail, you're looking at the one that gives you 5% in the tail. But obviously the direction matters then, so your p-values will change. Okay, I think I've got through those questions. If there's anything that I've missed, please do pop it back in there. I just want Dawn to be able to get going with her presentation, and then we can pick anything up on Dawn's, or if there's anything general at the end.
Thanks, Alice, and thanks very much to everyone for those really good questions. Let me just get my screen sorted out. Okay. Can't see anybody now. Let's just move you over here. Okay, so are you all able to see my slides?
Yes,
Thank
Dawn.
you.
Yeah.
Thanks. So this is quite a sort of specifically focused talk about the use of forest plots, and I think they're really useful when, as statisticians, as Alice has outlined, we like to encourage people to use more than the p-value, to see beyond the p-value and think about ways to summarize your results. And it can be very difficult compared to just a p-value to summarize the confidence interval and the point estimate following any sort of analysis. So I feel that the forest plots are an extremely useful way to communicate quite a lot of results all at the same time so that people can see all of that information. And so I hope by the end of today's talk, I've persuaded you a little bit as well. So the talk is in two parts. I'm going to give a little bit of an introduction as to where the forest plot has become most commonly used, and that's in systematic reviews and meta-analyses. And then the second part is just going to demonstrate some other uses and variations of this forest style plot, particularly when you use it for single study analyses as opposed to meta-analyses. And so just to make it clear what I'm actually talking about, in case no one's really sure what a forest plot is, here's an example of one, and I'm going to come back to this one later in my talk this morning. So basically the forest plot usually has information about characteristics of studies or information, so the sort of tabular form of information. And then there's also this visual representation of a comparative statistic following some analysis. So as Alice outlined in her talk, you get the mean difference and the confidence interval around it. And those characteristics are then plotted in the plot part of the forest plot on a common scale. So the people have been using these type of plots showing multiple things on the same graph for some time, but it's become called the forest plot and been made very, very popular in the evidence synthesis framework. And this has come about because as we've got more and more evidence being published, and we want to be fair to the evidence that is published, we need to have really good methodology to combine evidence from multiple sources. And I guess a few decades ago, it was more common to see sort of review style, open review style articles where there wasn't really any necessarily systematic way that particular parts of the literature were pulled together for a review. So it's become much more common now to require people to declare what's the basis of their review of the literature that they're presenting. And we've now got really well-developed, very flexible frameworks to support a systematic approach to literature review and evidence synthesis. So the meta-analysis part of the evidence synthesis is the statistical bit where you bring a large collection of analysis results from individual studies for the purpose of trying to integrate those findings. And that was first defined by Glass in 1976. So these, this sort of push to be more transparent, have unbiased and a transparent mechanism to do research has led to the whole systematic reviews and meta-analysis framework that is now very dominant in the literature. And if you want to know more about this framework and the toolkit that goes along with it, I can highly recommend the Cochrane material. They have really excellent online handbook which has very clear definitions of all of the concepts used and gives you a very clear pathway how these work. So in order to just outline to you what a typical systematic review and meta-analysis looks like, I've selected a very recent publication. It's fair to say this area of expertise is not mine, but I thought this might be a bit more appropriate for a lab studies focused talk. And I'm rather more used to looking at results from multiple clinical trials. But I felt that this was quite a nice one, and it also has a comparison of means as the effect size. So it ties in rather well with Alice's introduction. So this particular work is a systematic review and meta-analysis of this receptor IRAK3 and its action on inflammation in a number of models for the study of sepsis. So for this work, they have followed a fully specified, pre-specified protocol where they make it clear what literature they're going to search, what search terms they're going to use, and to make sure that they've got a fully reproducible process. And at the end of their abstract, they felt that they were able to make this conclusion that the meta-analyses confirmed the inhibitory effect of this receptor on TNF-alpha, mRNA, and protein expression after 2 specific challenges. So the next slide I've got here just shows the first part, the sort of literature, the systematic searching and filtering stage that goes on in a systematic review. You have the identification stage, the screening stage, the eligibility, and then finally the studies that are included. So you can see here that they'd identified a huge number of eligible studies in the first place. They went through a process of identifying duplicates, and then at the screening stage, they had almost 8,000 abstracts to review against their criteria, and these were done using four reviewers. So finally, they then, using various pre-specified criteria in the protocol, they ended up with 49 articles that met their criteria for the review. So they were actually looking at a variety of conditions and quite a lot of different models. So I'm only going to show you a very small fraction of the overall results of this publication. And so in this table here, their figure 2, we've got the first set of meta-analyses results. And these are 2 meta-analyses in this particular forest plot. So I'm going to take you through what the elements are, what's being presented in this forest plot, so that it's clear then how you can read the information. So as I said, there's two sets of results being presented on this single plot. So the first thing to identify is that for their condition 1, the 1.1.1 part, there are only 2 studies that met this condition, and hence they've summarized the features of those 2 studies there, and they've given them the identifiers. For the second set of conditions and models, they actually identified 6. So as you can see, some papers have got lots and lots of results that meet several of the conditions and the questions, and others have fewer. So even though they've got the 49 articles, they've got a different number contributing to each part of the result of the systematic review and meta-analysis. So along the top, we have the study identifiers down on the left in the rows, and along the top, we've got then the details of the 2 conditions. We've got control, and then those samples where there's been an intervention called a one challenge has been done on those particular samples. So we have breached the group. So we have our control and then our intervention group, and we have the group specific data is reported. So we have the means and the standard deviation and the total for each of the studies for each of the groups. And then below them, we actually see those data. So we can see here that there was sample sizes of 8 in each of these groups. And further down, we had, again, quite small sample sizes, but all of the group-specific information is revealed here. So the final, this final column is now the comparison between those two groups. So this is now the difference between the two group means with the 95% confidence interval. So these are the data that are extracted from the individual studies. And so this is just, effectively, this is like sorted the information into a table. So you can see the features of the individual studies and then the overall effect size reported for each of those studies in that column. And as you can see, it can be quite hard. If this was in a table, it'd be quite hard for you to look down this table to work out how similar or different these values were. And so it's really helpful to have on the final part of the table a visualization of the point estimate and the confidence interval shown in the visually adjacent to those quantities. And in the graph, those are shown in green. So what we've boxed in red here are currently shown in green at the end of the table. So the extra part then, which is where this is the meta-analysis part. We've used a method, or the authors rather have used a method to combine these individual study estimates to give an overall combined or pooled estimate. And they give a combined estimate and a confidence interval. And so what we have here is new data. So we have on that subtotal line, that's the overall estimate combining the two studies here on the top. And then there's an overall effect p-value, which for the top group is 0.03. And then there's an additional line here, which has heterogeneity information. So it's a big consideration when people are combining studies from different time periods or maybe slight variations between labs. There's always a check to see, are these results really more different than you'd expect by chance? And is it really fair to combine them in this manner? So there's always a heterogeneity check reported when there's a combined overall report. And it's fair to say, if there are concerns about the heterogeneity, then typically the pooled analysis will be left off the figure and the forest plot will only show the individual study effects. So I hope you can see from this figure then, because the confidence intervals and the individual values are represented by these squares here. So the square shows what's the relative weighting. The size of that square shows the relative weighting of that study in the final pooled analysis. And it helps you see, particularly if we're looking at the second one in this graph, of those 6 studies, all of the effects, even though some of them have got very, very wide confidence intervals, all of the effects are all above the null value, 0 difference. And they're all varying slightly. Some of them have got the wide confidence intervals because they're very small samples, but overall, we see quite, certainly in the group 2, we see quite a strong effect in favour of one challenge. So this addition of that final column with the visual representation of the confidence interval really helps you see all of the results, which are much more detailed in the actual table. So that was a bit of a rapid tour on how the forest plot is used to present results from many different studies and to communicate it to help people see where is the evidence coming from, how strong is the individual evidence, as well as showing you the overall effect size. So it's a really good way to communicate multiple confidence intervals, present you where the null hypothesis value would lie, and help you understand any justifications. So I'm going to move on. The second part of the talk is to show a really nice use of the forest plot, particularly in the results of the two results from the recovery trial. So the recovery trial was set up to evaluate treatments for COVID-19. It was set up a very, very innovative design for the time to be able to look at new potential treatments for COVID, open up new arms in the trial, and as soon as enough evidence was collected about a particular evaluation, they could report on that and continue the trial evaluating other arms. So it was a very nice dynamic design of a trial that was able to give very, very rapid and useful results. So I'm going to show how two of their outputs were summarized using forest plots. And if you want to know more about the recovery trial, they have a very nice website with their latest news. So the recovery trial, obviously it's one trial, but as I said, it's able to open new arms to evaluate new treatments in a dynamic manner. So I'm going to show you the results of two of the evaluations that they did. One was for dexamethasone and the other was for hydroxychloroquine, which I'm sure you were aware was getting a lot of attention in the media. And although the trial was able to look at multiple treatment options, it had exactly the same primary outcome, which was 28-day mortality for people recruited to the trial. And so to link back to how Alice framed the first lecture, there were sort of two separate research questions here. So the first one is, does dexamethasone decrease 28-day mortality in patients hospitalized for COVID-19 compared to usual care? And then the second question was exactly the same, but just for hydroxychloroquine. So I'm showing you part of the what's called the consort diagram here. So when the recovery trial felt they had enough numbers to ask the question for the dexamethasone treatment, they had, I hope you can see the numbers on this slide well enough. So they actually had just over 2,000 patients receive dexamethasone, and just over double that, 4,300 were assigned to receive usual care alone. And just to sort of show you the results in a raw form, when they looked at then the death rate within 28 days, the percentage of those then of each of those groups, there were 22.9% who died in the dexamethasone group and slightly higher number in the usual care group. So there was a difference of an absolute difference of 2.8% and slightly lower death rates in the dexamethasone group. So these, even though I've reported the data there as absolute risks and the risk difference, the data here, they knew exactly when the deaths had occurred, they knew when they had occurred. So this was actually survival data or time to event data, and it was analysed using Cox proportional hazards model. So what your summary statistic here is a risk rate, a rate ratio. But the way that you interpret the results is in the same manner. So we have a rate ratio reported here and a confidence interval to that effect. And what was interesting is that the recovery trial chose to present their main results and a subgroup analysis in a forest plot, which you can see here. So they've got the information from the group, some of that data I'd shown you before on the previous slide. So for all patients, if you just look at the bottom part of that forest plot, so we knew there was a sort of a 2.8% reduction in absolute risk. And when they applied the Cox regression model here, they got a rate ratio of 0.83 for the comparison of risk of dexamethasone versus usual care. And so you can see that the diamond in this case is going well below the null value of 1. If there was no difference between those treatments, we would expect the rate ratio to be very close to 1. But we seem to have evidence here that dexamethasone is definitely better. The p-value for that comparison is 0.0001. So it's very strong evidence against the null hypothesis. But on the forest plot, we've got the direction and the confidence interval around that measurement on the graph. So overall, there's very, very strong evidence that this is an effective treatment. However, when they went on to look at the subgroup analysis of these patients, so they split the patients by those who needed invasive mechanical ventilation or oxygen only, so they needed respiratory support. They found quite an interesting pattern, and there appeared to be a much stronger benefit in the patients that were more severely affected. So if you look at the results here, these are now the subgroups of all patients below. And for those who needed mechanical ventilation, there was a much stronger beneficial effect of dexamethasone. Even though the confidence intervals are quite wide, the effect size is about 0.6. So the whole range of values where we think the true value might lie are all in the very, very beneficial range. Those patients who did only require oxygen also seem to get a statistically significant benefit from this treatment. But for the patients who didn't require oxygen, actually the point estimate is lying on the side of the line that suggests that usual care is better, but the confidence interval includes 1, which is our rate ratio here. And so this was interpreted as, in fact, there was really not sufficient evidence of the benefit for patients who didn't need any required respiratory support to receive dexamethasone. And I think it's quite interesting to look. So even though the confidence interval includes the null value here, and hence our p-value for that comparison from Alice's slide would definitely be greater than 0.05, actually, because the confidence interval is very limited into how much benefit dexamethasone may have, this was felt to be a lack of evidence of the benefit of dexamethasone for this group of patients. So that result changed practice immediately, and dexamethasone was then given to patients that needed respiratory support. So the other result from the recovery trial then was looking at hydroxychloroquine. And again, they had an arm in the trial that was randomizing patients to this intervention. So when they stopped the arm for the hydroxychloroquine, they had 1,500 patients compared to just over 3,000 And this time, if you look at the outcome, so we've still got mortality within 28 days, we've actually got slightly higher death rates in the hydroxychloroquine group than the usual care. And in this case, when they produce the results, again, they've shown some subgroups, but on this graph, they've shown multiple subgroups within the patients. So again, at the bottom, you've got all participants, and when they used a survival analysis appropriate method, here their rate ratio actually showed that the point estimate was actually in the usual care direction, and the confidence interval just covered the null value, and the confidence interval went as low as 0.097 in favour of hydroxychloroquine, but the p-value there was 0.015. So the way that they've organised the forest plot in this case is they've shown multiple subgroups sort of stacked on top of each other to highlight splitting the patients by many different ways. And what you can see by looking at the multiple different ways of looking at the patients, there's really very little evidence of variation in this effect. So on the whole, it looks that hydroxychloroquine could be potentially a little bit more harmful than usual care, but there's certainly no evidence, not sufficient evidence that there's any benefit. So again, this is a way of showing you multiple results, so you can see all the details of the numbers if you want to, but the fact you've got this visual aid of a confidence interval in the middle of the table just really helps you make sense of all of this information all at once. And in this graph, they've also used the size of the square to indicate the sort of the amount of patients, the weight of that subgroup in the overall patient population. So I gave a bit of background there about the use of using a forest plot to communicate results within a single study, but when you want to show multiple subgroups. Now I've got an example here of a further extension to a forest plot type presentation. This is a very different use of a forest type plot. Here we have, there's been a reanalysis of this trial data, a secondary analysis of trial data to look at health transitions in older people. So these are, what we've got here on the rows are changes in state. So from healthy to cancer, from healthy to cardiac events. And the multi-state model that they've applied has then given these transition probabilities, and these are then presented as hazard ratios. So these are all different rates presented as the rows, but they've actually used, one of them is contrasting the age, and the other one is contrasting men and women. And so here they've not only got the hazard ratio and the confidence interval, they've also chosen to add in the p-value. So again, this allows you to compare lots of probabilities from the multi-state model on one particular graph. So there's really, given that the main benefit from my point of view of the forest plot is it enables you to have a visual aid for people. You've got all the detailed figures in a table, and it just allows you to show it visually, so it's much more easy for you to see it all at the same time, because people really struggle to take in more than one statistic when it's written in a paragraph, and even when it's presented in a table, it can still be very difficult. So there's there's many other ways that a forest type plot can be very, very useful in communicating results. I've only shown here how to show how to highlight subgroups within a single study today, but there's also many other ways it can be used. In clinical trials, we often have like our primary analysis, which is like the intention to treat. So everybody in the trial is included, no matter what has happened to them, if they were given the wrong medication or whatever. You have the intention to treat analysis, but then you can have a number of either subpopulations or sensitivity analyses shown in a table and then presented as a forest plot to show, well, what happens if we remove the patients that crossed over, for example, or the patients where their measurements were taken at the wrong time. We can see how much our conclusions change, how much the confidence interval changes and the point estimate changes when we use these slightly different conditions. And it can really be very helpful to show you, have you got a borderline result that's very, very sensitive to your assumptions, or have you got a really robust result that no matter what you do, you get very, very similar results. I've also seen examples of this where you can look at multiple outcomes for a single study. So Alice was pointing out how it's important whether you have a continuous outcome or a binary outcome, because you summarize and analyze this in different ways. But it could be that in particular studies, you might have multiple outcomes being measured. So there may be multiple questionnaires, for example, and if you organize the outcomes so you're clear which is a benefit, which is a beneficial result and which is a poorer result, you can actually present multiple outcomes on a forest plot too, although the scale won't necessarily mean the same thing. And there's a very nice article in the Journal of Clinical Epidemiology that shows a lot of really nice uses of forest plots. So the final thing that I just wanted to say is that it's actually quite easy to create your own forest plots. It's possible to do them in Excel by some sort of tricking some of its default settings to do a forest plot. It's actually quite easy in most packages to do the sort of visual display part of the forest plot. If you want to produce the full structured table, such as I've been showing here, where you have a lot of information about the components of the trial, you'll probably need to use a more specific piece of software, such as the RevMan, which comes as part of the meta-analysis suite, or one of the many R packages that enables you to draw forest plots, such as RMeta in R. So I hope I've encouraged you to think about using a forest plot in some of your future work. And that's the end of my talk. Thank you.
Thank you, Dawn. Do you have any questions in the chat for Dawn? Dawn, has anyone sent anything directly to you? I haven't got anything.
No, I can't see anything in the chat.
Okay. Are there any other questions? Potentially more general questions, if anyone would like to ask those in the chat, or if you want to just put your hand up and we can go through some of those. I mean, alternatively, if people don't have questions, the other thing that would be really good to know is if this has been useful, and if there are any other topics that you would find useful for us to cover in future events. We're quite happy to look at putting some more of these together in the future if they are of use to you. Okay, what I'll do is I'll put my email address into the chat box, and if anybody does have anything that they would like to provide in the way of feedback or suggestions for future events, or there's some, then that would be great. So I'll put my if you have any thoughts after this session, then please do let me know. Okay, thank you. That sounds really positive from anyone. Yeah, any other topics? I think it's certainly sample size was perhaps coming through as something that people might find useful to know about. So if you agree with that, please do indicate that in the chat or let us know in some way. And we can certainly look to develop more sessions based on any feedback we get.
Thanks, everyone. Some very, very nice feedback.
Analysing a research paper as a future topic. Do we have the link to the YouTube channel? So I think that's from the, I don't have that link at the moment. Sample size would be good.
Yeah, well,
it's from the NIHR stats group, isn't it?
It's currently in progress, the YouTube channel. We had a bit of problem with it recently, but what we'll, because these recordings can end up being very, very large files, it's preferable for us to load it up onto YouTube and send the link, but we'll put it on the stats group page so you can find it that way. But I think it should be possible, Alice, to email everyone who's registered today the link when we have it set up. It's a hidden channel, so you can't search for it, but we can let you have it.
Yeah, okay, we'll email the link out to everyone when we've got that. Thank you. Analysing a research paper as a future topic. Okay.
What is the stats group page? Can I find that?
You got that to hand on?
I should have. I can't get my yeah. Bottom of the thing, shouldn't we? Here we go.
I've got it now. Have you got it?
I've got it. Here we go. I think it's possible we didn't even have today's event listed on the. We didn't have today's event listed on our events because we sent it because the way we sent the events out.
Yeah, so this session was very much targeted at people that would find this information useful, or those that we thought we'd find that information useful. But I think it's obviously we've had a good turnout. There seems to be lots of appetite for this session, so I'm happy to think about, you know, this being a series where we can offer other things as and when people need them. Okay, so that seems really good then. I think we've got a few ideas, but please do drop me a line if anybody has any additional feedback or suggestions for new sessions. Otherwise, are we happy to leave it there, Dawn?
I think so. Less is more.
Okay, thank you ever so much for coming to the session today. It's been really good and we had some really great questions, so thank you for that.